Welcome to this problem-solving session. Today, we'll be tackling the problem number 994, rotting oranges. This is a classic grid-based problem that challenges us to simulate the spread of rot among oranges over time. Let's explore how to break it down step by step and solve it efficiently. In this problem, we are given a grid where each cell can take one of three possible values. A value of 0 represents an empty cell, meaning nothing is there. A value of 1 represents a fresh orange, which is an orange that is still good and hasn't rotted yet. Lastly, a value of 2 represents a rotten orange, which is an orange that has already gone bad. The key dynamic here is that every minute, any fresh orange that is directly adjacent to a rotten orange in one of the 4 cardinal directions, up, down, left, or right, will also become rotten. The goal is to determine the minimum amount of time required for all fresh oranges to rot. If there are any oranges that cannot possibly rot because they're isolated or unreachable, we will return -1. The input will always be a 2D grid of integers, and the output will be a single integer representing the time required or -1 if it's impossible to rot all oranges. Let's take a look at an example to understand how the process works. Suppose we have the following grid, 2 1 1 1 1 0 0 1 1. At the start, there's one rotten orange at position 0 0, and several fresh oranges surrounding it. The goal is to determine how long it takes for all the fresh oranges in this grid to rot. Initially, in minute 0, the grid remains unchanged as no time has passed yet. The rotten orange at 0 0 has not yet spread its rot to the adjacent fresh oranges. As time progresses, the rotting spreads. In minute 1, the rotten orange at 0 0 infects the fresh oranges directly next to it. This results in 2 more oranges becoming rotten, and the grid now looks like 2 2 1 2 1 0 0 1 1. By minute 2, the newly rotten oranges from the previous step infect their adjacent fresh oranges. The grid updates to 2 2 2 2 2 0 0 2 1. In minute 3, the rot spreads further, and the grid becomes 2 2 2 2 2 0 0 2 2. Finally, by minute 4, no fresh oranges are left in the grid, meaning all the oranges have rotted. The minimum time required to achieve this is therefore 4 minutes, which is the output for this example. Now consider another example to understand a situation where it is impossible to rot all the oranges. Suppose the grid is 2 1 1 0 1 1 1 0 1. Here, while some fresh oranges are reachable by the rotten orange at 0 0, there are others, such as the orange at 2 2, that are completely isolated. No matter how much time passes, the rot will never be able to reach these isolated fresh oranges. As a result, the output in this case is -1, indicating that it is impossible to rot all the oranges. In a simpler scenario, let's look at the grid 0 2. Here, there are no fresh oranges in the grid to begin with, only one rotten orange is present. Since there's nothing to rot, the minimum time required is 0. This highlights that if there are no fresh oranges present in the grid initially, the problem is already solved, and the output is simply 0. The constraints of the problem ensure that the grid size is small, with dimensions up to 10 by 10, making it manageable to analyze and solve. To summarize, there are a few edge cases to keep in mind. If there are no fresh oranges in the grid from the start, the output should always be 0 because there's nothing to rot. On the other hand, if all oranges are fresh and there are no rotten oranges to begin with, the output should be -1 since there's no way for the rotting process to start. The problem is designed such that the grid size is small enough to efficiently solve using a breadth-first search approach, which ensures that we can explore all possible paths for the rot to spread within the given constraints. To solve the rotting oranges problem, we initially considered a brute force approach. The intuition here is straightforward: for every time unit, manually simulate the spread of rot. Starting with the rotten oranges, we would check all their neighbors up, down, left, and right for fresh oranges and rot them. This process would repeat until no fresh oranges remain. The implementation involves nested loops to iterate over the grid at each time step, keeping track of which oranges rot during each iteration. However, this method is highly inefficient. Since the grid needs to be scanned repeatedly, the time complexity becomes O, open parenthesis m times n close parenthesis squared, where m is the number of rows and n is the number of columns. For larger grids, this inefficiency becomes a major drawback, making brute force impractical. While it's an intuitive starting point, the repeated scans and lack of optimization make it unsuitable for our needs, especially when faster alternatives exist. Instead, we opted for an optimized approach using breadth-first search, or BFS. Here, we treat the grid as a graph, with each cell acting as a node and edges connecting adjacent cells. The rotten oranges, which initially have a value of 2, form the first layer of the BFS. During each step of the BFS, the rot spreads to any adjacent fresh oranges, represented by a value of 1. This method ensures that the rot propagates layer by layer, allowing us to count the time taken for all fresh oranges to rot. To implement this, we start by adding the positions of all initially rotten oranges to a queue. At each step, we dequeue all the rotten oranges at the current level, spread the rot to their fresh neighbors, and enqueue those newly rotten oranges. We continue this process while tracking the time required for each level of BFS. Finally, we check the grid to see if any fresh oranges remain. The BFS approach is efficient, as each cell in the grid is processed at most once. This results in a time complexity of O(m*(n), where m and n are the dimensions of the grid. The space complexity is also O(m*(n), due to the queue used for BFS. This balance of simplicity and efficiency makes BFS an excellent fit for the problem. Another alternative we explored was a depth-first search, or DFS-based approach. With DFS, the idea is to use recursive calls to propagate the rot from each rotten orange to its neighboring fresh oranges. This approach can also track the maximum time taken for the rot to spread throughout the grid. The implementation involves writing a recursive function that spreads the rot to adjacent cells and updates the time taken accordingly. While the time complexity of DFS is still O(m*(n), similar to BFS, it has some practical drawbacks. Recursive calls can lead to stack overflow issues, especially with large grids. Additionally, DFS is less intuitive when trying to simulate the layer-by-layer propagation of rot, which is a natural fit for BFS. These limitations make DFS less efficient and harder to implement effectively for this specific problem. Ultimately, we chose the BFS-based approach as the best strategy for solving this problem. By modeling the grid as a graph and using BFS, we can simulate the rot spreading in a systematic, level-by-level manner. This corresponds directly to the time it takes for the rot to propagate, making BFS a natural fit for the problem. Unlike brute force, BFS avoids redundant checks and is far more efficient, with a time complexity of O(m*(n). Compared to DFS, BFS is more robust for handling large grids because it doesn't face recursion depth limitations. It also provides a clear and organized way to track both the progression of rot and the elapsed time. This balance between clarity, performance, and scalability makes BFS the optimal solution. By leveraging its efficiency, we can confidently handle even the largest test cases within reasonable time limits, ensuring our solution is both practical and reliable. To solve the rotting oranges problem, we first need to understand the setup. The grid contains 3 types of cells: fresh oranges represented by 1, rotten oranges by 2, and empty cells by 0. Our goal is to calculate the minimum time it takes for all fresh oranges to rot. If there are unreachable fresh oranges, we return -1. The algorithm begins by initializing the grid and preparing for a breadth-first search, or BFS. First, we scan the grid to identify all initially rotten oranges and add their coordinates to a queue. This queue will allow us to process the rotting oranges layer by layer. At the same time, we count all fresh oranges in the grid, which helps us track when the process is complete. Finally, we introduce a variable, time, to measure how many minutes have passed during the rotting process. With the setup complete, we now prepare for the BFS to simulate the spread of rot. The next step is to simulate how the rot spreads across the grid. Using the BFS approach, we process all the rotten oranges in the queue, layer by layer. Each layer represents oranges that rot within the same unit of time. For every rotten orange processed, we check its neighbors in all 4 possible directions: up, down, left, and right. If a neighboring cell contains a fresh orange, we convert it to rotten by marking it as 2, add its position to the queue, and decrement the count of fresh oranges. After processing all oranges in the current layer, we increment the time counter to reflect the passage of 1 minute. Once the BFS completes, we check the final state of the grid. If there are still fresh oranges remaining, it means some oranges were unreachable, so we return -1. Otherwise, we return the total time taken to rot all oranges. BFS is particularly well suited for this problem because it processes nodes at the same distance from the source simultaneously, which mirrors the real-world spread of rot. BFS is the ideal choice for this problem because it guarantees the shortest path or minimum time to spread the rot across the grid. Unlike depth-first search, BFS ensures that all adjacent oranges are processed simultaneously, which matches the problem's dynamics. There are a few edge cases to consider. If there are no fresh oranges in the grid initially, the time required is simply 0 since no rotting is necessary. If there are fresh oranges but no rotten ones to start the process, we immediately return -1 because it's impossible to rot all oranges. In the case of an empty grid, we also return 0. The algorithm relies on 3 key data structures: the grid itself, which lets us track the state of each cell in constant time, a queue, which organizes the BFS process efficiently, and a fresh counter, which helps us determine when all fresh oranges have rotted. Analyzing the complexity, the time complexity is O and *m, because we process each cell at most once, and the space complexity is also O and *m in the worst case, when all oranges are rotten and stored in the queue. Let's work through an example to see the algorithm in action. Suppose the input grid is as follows: 2, 1, 1, 1, 1, 0, 0, 1, 1. First, we identify the initially rotten oranges. In this case, there's only one at position 0, 0, so our queue starts as 0, 0. The fresh orange count is 5, and the time starts at 0. Now, during the first minute, we process the orange at 0, 0. Its neighbors 0, 1, and 1, 0 are fresh oranges, so we rot them and add them to the queue. The queue becomes 0, 1, 1, 0, and the fresh count decreases to 3. Moving to the second minute, we process 0, 1, rotting its neighbors 0, 2, and 1, 1. Meanwhile, processing 1, 0 rots 2, 0. At this point, the queue contains 0, 2, 1, 1, 2, 0, and the fresh count is down to 1. In the third and final minute, we process the remaining oranges in the queue. The last fresh orange is rotted during this step, and the fresh count reaches 0. The queue at this point becomes empty, and we can return the total time taken, which is 3 minutes. If any fresh oranges had remained after processing all rotten oranges, the algorithm would have returned -1 instead, indicating that not all oranges could rot. This step-by-step simulation demonstrates how BFS ensures that the rot spreads evenly across the grid, with each layer of processing corresponding to 1 unit of time. By the end, we achieve an accurate and efficient solution to the problem. To solve the rotting oranges problem, we start by importing the D class from the collections module, which will help us implement a breadth-first search, or BFS. Inside the oranges rotting function, we begin by determining the number of rows and columns in the grid, and we create a queue to store the positions of all rotten oranges along with their respective timestamps. We also initialize a counter to track the number of fresh oranges in the grid. Next, we loop through each cell in the grid. If a cell contains a rotten orange, represented by the value 2, we add its coordinates and an initial time of 0 to the queue. If a cell contains a fresh orange, represented by the value 1, we increment the fresh_oranges counter. This setup ensures that we have all the initial conditions necessary to process the rotting process. After initializing the queue and counting fresh oranges, we define a list of directions for the 4 neighboring cells: right, down, left, and up. This will help us explore adjacent cells during our BFS. Finally, we initialize a variable called time_elapsed to track the total time taken to rot all the oranges. The while loop processes each rotten orange in the queue, beginning with the starting set of rotten oranges, and explores its neighbors to check if fresh oranges can be turned rotten. Now, inside the while loop, for each rotten orange we dequeue, we iterate through its 4 possible neighboring cells using the defined directions. For each neighbor, we ensure it is within the bounds of the grid and check if it contains a fresh orange. If we find a fresh orange, we update the grid cell to 2, marking it as rotten. We also decrement the fresh_oranges counter and add the neighbor's position and the updated time to the queue. This process continues until all reachable fresh oranges are processed, or the queue is empty. After the BFS completes, we check if there are any remaining fresh oranges. If the fresh_oranges counter is 0, it means all oranges have successfully rotted, and we return the total time_elapsed. However, if there are still fresh oranges left, we return -1 to indicate it's impossible to rot all the oranges. This ensures that our function handles all edge cases, such as isolated fresh oranges, correctly. Here, we begin by importing the necessary libraries and defining our solution class. The method oranges rotting takes a 2D grid as input, where each cell represents the state of an orange, 0 for empty, 1 for fresh, and 2 for rotten. To start, we determine the number of rows and columns in the grid. We also initialize a queue to help with breadth-first search, or BFS, and a variable fresh oranges to keep track of the total number of fresh oranges. Next, we iterate through the grid to identify all rotten oranges, adding their positions and an initial time of 0 to the queue. At the same time, we count the total number of fresh oranges. This setup ensures that we can begin spreading the rot from all rotten oranges simultaneously. Additionally, we define the possible directions for adjacent cells, right, down, left, and up, which will help us explore neighbors in the BFS process. Finally, we initialize the time-elapsed variable, which will track how many minutes have passed as the rot spreads. Now, we process the queue using a while loop, performing the BFS to spread the rot. For each rotten orange, we extract its position and the time it took to reach this orange. Then, we iterate over all 4 possible directions to determine the positions of adjacent cells. For each neighbor, we check whether it is within the grid boundaries and if it contains a fresh orange. If these conditions are met, we rot the fresh orange by updating its value to 2, decrement the fresh oranges count, and add the new position along with the updated time to the queue. This ensures that the rot continues spreading outward. Once the queue is empty, meaning all reachable oranges have been processed, we check if any fresh oranges remain. If fresh oranges is 0, we return the total time elapsed, which represents the time required to rot all oranges. Otherwise, if there are still fresh oranges, we return -1 to indicate that not all oranges could be rotted. To solve the rotting oranges problem, we start by initializing key variables. Here, the grid has 3 rows and 3 columns. We use a queue to store rotten oranges along with their time of rotting, and a counter for fresh oranges. As we traverse the grid, we find a rotten orange at position 0, 0, and add it to the queue with a time of 0. For fresh oranges at positions 0, 1, and 0, 2, we increment the fresh orange counter. Continuing through the grid, we find more fresh oranges, bringing the total count to 5. At this point, the queue contains 1 rotten orange at 0, 0, and we are ready to begin the rotting process using breadth-first search, or BFS. The BFS process starts with the rotten orange at 0, 0, and time 0. We check its adjacent cells. The orange at 0, 1 is fresh, so we rot it, decrement the fresh orange count to 4, and add it to the queue with a time of 1. Similarly, the orange at 1, 0 is fresh, so we rot it, decrement the count to 3, and add it to the queue with a time of 1. The grid now reflects these changes. Next, we process the orange at 0, 1, which is at time 1. Its adjacent fresh orange at 0, 2 is rotted, and the changes are reflected in the grid. The BFS continues, rotting oranges layer by layer, until no fresh oranges remain. Once the BFS completes, we perform a final check. Since the fresh orange counter is now 0, it means all the oranges have rotted. The total time elapsed during this process is 4 minutes, which we return as the output. This completes the first example where all oranges could be rotted in the minimum time. In the second example, all the oranges in the grid are already rotten. During initialization, the queue contains all the rotten oranges, and the fresh orange counter is set to 0, because there are no fresh oranges. When BFS is executed, the queue processes the rotten oranges, but since there are no fresh oranges to rot, the grid remains unchanged. After the BFS, we find that the fresh orange counter is still 0, so the time elapsed is 0. This result makes sense because no additional rotting was required. In the third example, not all oranges can rot because some fresh oranges are isolated. During initialization, we find 1 rotten orange at 0, 0, which is added to the queue, and 5 fresh oranges. The BFS starts by rotting adjacent oranges, updating the grid. However, certain fresh oranges, like the one at 2, 2, are unreachable due to obstacles or being surrounded by empty cells. After BFS, the fresh orange counter is greater than 0, indicating that not all oranges could rot. In this case, we return -1 as the output to signify that it is impossible to rot all the oranges in the grid. To analyze the time complexity of the algorithm, we start by noting that the grid has dimensions n rows by m columns. During the initialization phase, the algorithm iterates over every cell in the grid to count the number of fresh oranges and enqueue the initially rotten ones. Since this requires visiting each cell exactly once, this step takes n*m time. Next, during the BFS traversal, each cell is processed at most once, either when it is initially rotten or when it becomes rotten during the propagation. For each cell, the algorithm checks its 4 neighbors, which is a constant time operation. This means the BFS step also takes n*m time in total. Finally, there is a single check to determine if any fresh oranges remain, which is an O1 operation. When we combine these steps, the overall time complexity is dominated by the grid traversal and BFS, resulting in n*m. Now, looking at the space complexity, the algorithm requires n*m space in the worst case. First, consider the queue used during BFS. If all oranges in the grid are rotten or become rotten, the queue could hold up to n*m entries at its maximum, leading to n*m space usage. The input grid itself also requires n*m space, but since the algorithm modifies the grid in place, no additional space is used for a separate data structure. Additionally, the directions list used to determine the neighbors of a cell is fixed in size, containing 4 entries, so it only requires O1 space. When we consider these together, the space complexity is dominated by the queue, resulting in n*m. The algorithm's behavior can be better understood by considering the best, average, and worst-case scenarios. In the best case, all oranges are already rotten, meaning there are no fresh oranges to process. Here, the BFS does no work beyond initialization, and the time complexity is n*m, due to the grid traversal during initialization. In the average case, where the number of fresh and rotten oranges is relatively balanced, BFS processes only a subset of the grid, but the overall time complexity remains n*m. In the worst case, nearly all oranges are fresh except for one that is initially rotten. BFS then traverses every cell in the grid, leading to n*m time complexity. In all cases, the time complexity remains linear with respect to the size of the grid. When comparing the BFS approach to a naive solution, the difference in efficiency becomes clear. A naive approach might involve repeatedly scanning the grid to rot adjacent oranges layer by layer. Each scan of the grid takes n*m, and in the worst case, this process could repeat n+m times, resulting in a time complexity of n+m*n*m. This is significantly less efficient than the BFS solution. The optimized BFS approach ensures that each cell is processed only once, achieving a linear time complexity of n*m, which is optimal since every cell must be considered at least once. Mathematically, the BFS approach guarantees that the total number of visits is bounded by n*m, with constant time neighbor checks for each cell. This ensures both the time and space complexities remain n*m, making this approach the most efficient solution for the problem. When working on the rotting oranges problem, there are a few common mistakes to watch out for. First, not considering edge cases like boundaries or empty grids can lead to runtime errors or incorrect results. For example, forgetting to handle an empty grid or a grid with no fresh oranges might cause your solution to crash or return unexpected outputs. The fix is simple: always test your solution with corner cases, such as an empty input, a single orange, or a grid where all oranges are already rotten. Another common issue is modifying the grid while iterating through it. This can create unintended side effects, like prematurely marking an orange as rotten, which then affects subsequent iterations. A better approach is to use a separate queue or data structure to track changes and apply them only after processing the current state. Lastly, failing to check all neighbors, such as missing one of the 4 possible directions up, down, left, or right, can result in fresh oranges being incorrectly preserved. To avoid this, always ensure you loop through all 4 directions, using either a helper array or coordinate offsets to simplify the implementation. Another potential pitfall is falling into infinite loops due to cyclic dependencies. This happens when cells are revisited without proper tracking, or when the state of a cell is updated incorrectly. To prevent this, you can use a visited set to keep track of processed cells, or make sure that each cell is processed only once after its state changes. Timing issues are also a frequent mistake. Mismanaging the time counter might cause you to either overestimate or underestimate the time required for all oranges to rot. The best practice is to increment the time counter only after finishing the processing of all oranges in the current layer of the breadth-first search. This ensures an accurate calculation of how many time steps it takes for the rot to spread completely. In interviews, it's important to focus on using breadth-first search, or BFS, as it's the preferred approach for solving problems that involve spreading or shortest paths. BFS works well here because it explores all neighbors layer by layer, mimicking the way rot spreads in real life. A useful mental model is to think in layers, processing one layer of spreading rot at a time. This approach not only makes it easier to manage the time steps but also helps you visualize the process clearly. Edge cases are another area interviewers often focus on, so it's vital to handle situations like all rotten oranges, no fresh oranges, or fresh oranges that are disconnected from the rotten ones. Lastly, while optimizing space, you might consider modifying the grid in place to reduce auxiliary space usage. Just be careful to avoid interfering with ongoing iterations, as it might lead to incorrect results. If you're preparing for this problem, you can also explore related problems. For example, LeetCode 286, Walls and Gates, and LeetCode 542, O1 Matrix, both use BFS for grid traversal. For a more advanced challenge, check out LeetCode 1293, Shortest Path in a Grid with Obstacles Elimination, which adds additional constraints to BFS-based solutions. There are also alternative approaches to solving this problem, each with its own trade-offs. A brute force simulation is the simplest method but comes with a significant drawback: it's highly inefficient, with a time complexity of O, open parenthesis n times m close parenthesis squared. This is because it recomputes neighbors for every rotten orange at each step. A much better option is breadth-first search, which is more efficient with a time complexity of O, n asterisk m. BFS uses a queue to track rotten oranges and is generally the most space-efficient approach for this problem. Depth-first search, or DFS, can also be used to explore the grid, but it's less intuitive for time tracking in this specific scenario. Additionally, DFS risks stack overflow for large grids, making it less suitable here. Finally, there's the advanced option of using UnionFind to model connected components, though this is generally overkill for rotting oranges. It's also less intuitive and harder to implement compared to BFS. Overall, BFS strikes the best balance between simplicity and efficiency for this problem. Great job! We've covered the key ideas behind solving the rotting oranges problem. BFS turned out to be the optimal approach for this grid-based simulation. Remember to practice similar problems to strengthen your graph traversal skills. Thanks for watching, and don't forget to like, share, and subscribe for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!